Today we're going to talk about, we're going to hopefully finish up the discussion on AR. In this case, we're talking about tracking and reconstruction. And yeah, we only have next week left, and next week will be just finishing things up mostly. Next week will just be, what were the topics for next week? Haptics, olfactory displays, and some other displays that are kind of similar to VR, but maybe aren't exactly what you would expect to be considered VR, like caves. And the next Friday lecture should be really interesting. At least I've never seen a lecture like it before, where I will describe to you how research in AR and VR actually works, and how you can make your work actually mean something instead of being a class project. But anyway, moving on, today we'll go over topics such as tracking, 3D reconstruction, and how we figure out where these devices are, such as the Quest, which doesn't require any external trackers, which is actually new for VR, but it's not really new for AR. AR has always kind of made the assumption that you shouldn't have any wires on a headset that you expect people to go around in public with, or just, devices that you want to be portable. The whole point of AR is that it was meant to be, AR was meant to be brought with you, basically. So you can check out the old lectures. I know on Wednesday I overslept quite a bit, but I did record the lecture and I posted it, so you can check out the topics that we talked about last time if you think you missed anything. On Monday we talked about some different types of AR displays. In particular, we care about near-eye displays, which are the HoloLens and Magic Leap. And we care about these because they can be really compact, and the lighting technology is really complicated, but they are just more ergonomic and more feasible for any future AR research. And we talked about some really awful near-eye displays, or not awful, but near-eye displays that aren't meant for any kind of 3D space understanding. Some challenges we talked about. On Monday we ended talking about the field of view problem, and it is definitely a problem. AR devices have tiny fields of view. And on Wednesday I talked about some multifocal displays, which are these displays that have multiple combiners so that each combiner only reflects part of the image at different depths, and your eye focuses on it. So you can check out the video for more information about that. I talked about light field rendering, which is a slightly more dynamic and stable approach to this depth of field problem, where they essentially render the image, then subdivide it into a bunch of small parts, and then apply some filter to each of those small parts, such that when your eye focuses on one of these parts, like say that you want to focus on the top right of this image, your eye will naturally defocus the other parts. It works very similar to HRTFs in audio, where you're basically predicting what the audio will sound like, giving your head shape and things like that. Other things like that. And there were some resources on light fields that you can check out if you're interested. I briefly went over volumetric displays, which are kind of rare, but they're cool. And if I have time next week, I might explain a little bit more how they work, but they're basically the only existing real hologram. And what they do is they are displays that are designed to reflect or scatter light such that it creates a sort of 3D pixel, so that anybody from any viewpoint would see this pixel and see some 3D object. And these are called autostereoscopic displays because you don't need to be wearing a headset to see the 3D effect. And you can check out the videos if you're interested. Most of what I talked about on Wednesday was how the physics behind displays work. So we talked about distortion and how lenses deal with distortion problems. In AR, it's harder because we want to design displays that don't distort the real environments, but distort or undistort the virtual environments, so that it reflects onto the combiner correctly. And there are a couple of ways you can do it. Near-eye displays like the HoloLens, they do it all in the combiner basically, but they're actually a little bit more complicated than that. I explained how you calculate distortion, which is close to where I stopped. And generally, distortion is calculated by defining a marker, for example, a checkerboard, which you know the shape of without distortion, and then you calculate an equation or a matrix that you need to undistort it. So checkerboards are easy, for example, because you just figure out how you turn these into lines. So again, you can check out the old lecture on that. And I explained how intrinsic calibration works and extrinsic calibration. Some common markers are things like the checkerboard, which is really simple, but it's hard to orient because you can rotate this a couple of different ways and it will still look the same. Aruka markers are really popular because they have a lot of the benefits of checkerboards, except you can also orient them. Charuka markers are becoming popular because you can kind of divide the task of handling the intrinsic distortion and the orientation. Some other APIs, like the ones that we see on that are popular on the HoloLens and Magic Leap, use image targets, which have a lot of features, and it finds feature correspondences. More we'll see in a little bit. More recent implementations have been trying to track 3D objects, except it's hard because, well, why it's hard will hopefully become more intuitive today as we talk about reconstruction, but it's actually pretty hard to figure out what the features of a 3D object are, and how you make the feature of the 3D object unique compared to the 3D features of other objects that are in the scene. It's just a complicated problem in general. And finally, I talk about defocused markers, which are markers that deal with this problem or they attempt to deal with this problem that when you put an image very close to the camera, it will start blurring. And there is this cool paper on dealing with this problem. I've actually used this idea before to just, like with image targets, for example, what I've done before is just apply a bunch of blur to the image and then give it to the API so that it knows what the blurred image looks like as well as the crisp one. I talked about some common APIs, the ones that matter the most for most people, especially in modern AR and VR, like the HoloLens Magic Leap or OpenCV and Vuforia. OpenCV is this really common open source library, has tons of example code. It is very hardware intensive and it doesn't do many things very quickly. I think partially because a lot of its stuff is only single threaded, which makes things harder. These other APIs are actually, they use a lot of ideas from OpenCV, except they handle this hardware intensity problem a little bit better. Vuforia is really popular on the HoloLens especially, because it's really, really good for some reason at handling occlusion. Unfortunately, it's proprietary, so we don't really know why it's so good at handling occlusion, but it is. Occlusion is, when the marker is partially blocked, which is obviously going to be a problem because there are so many things that can block markers, like your hands, controllers, the headset itself, that the occlusion actually does make a difference. And in my experience, Vuforia is by far the best at handling occlusion. And it also doesn't require manual camera calibration. I'm hesitant to recommend it as a general strategy because it is proprietary, which means that you can only do so many things with it. But for what it was meant for, it's really, really good at. If for general purpose computer vision, OpenCV is the most common. Now, what I didn't get to last time, which we can talk about now, is tracking. So, like in VR, especially these more recent VR devices which can track in 6 degrees of freedom without any external trackers like the Quest, AR devices need to know where they are so that you know where essentially to move the camera in the 3D virtual environment. For example, as you know, when you move your head in the Oculus Quest, it moves your camera in Unity. So AR devices, like I said, have already made this assumption that you shouldn't have any external tracking ability because AR devices are meant to be, they're meant to blend with the synthetic or with the real world synthetically so that people could use them in their day-to-day lives. So if you have external trackers, you obviously can't really do that. And the Quest is arguably the first consumer device in VR that made this assumption as well. I'll show this in the next slide, but if you recall the Oculus Tracking paper that we talked about a while ago, the rotational part of the tracking can actually be handled mostly by the internals. For example, accelerometers, gyroscopes, IMUs, things like that. We still need to correct it to some extent, partially because AR devices can only track at so high of a frequency, and we'll see in a second, but a lot of these devices like gyroscopes, accelerometers, etc., they measure deltas, which means that any error in a single measurement will propagate. Any like translation or rotation is a lot harder because there aren't many devices that can actually accurately measure translation. Accelerometers can kind of do it, and IMUs are more complicated and they include accelerometers usually, but even they have problems with this propagation. So here's the comment that's talking about the same problem. You can do it with IMUs, like this is the IMU that was used in Apollo 11 that includes things like gyroscopes, accelerometers, and so on. IMUs are basically just these devices that are filled with a bunch of individual tracking devices which track different things and pool the results somehow. And they pretty much always measure deltas, so how much did you translate in a single frame, or how much did your acceleration change, how much did your rotation change, so on. The problem is that if you're measuring deltas, if you have like a sequence and there's some error in the middle of the sequence, the error is going to be preserved in all of the deltas that are upcoming, which becomes a problem because it just propagates over and over again. Or it propagates through the entire future sequence if you don't correct it somehow. There's this cool implementation that I'll show in a second where they actually tracked this. They used IMUs to track some person walking throughout an entire city really accurately using a combination of Google Maps, I think, or OpenStreetMap or something like that, plus IMUs. And in this case, they were using Google Maps or OpenStreetMap to correct any of the delta problems. I believe that's how it worked. I don't remember exactly the details of the paper. Like I said, deltas accumulate. And the way that we normally deal with this instead is by using cameras and reconstructing things. So here's the Foxley. Well, this wasn't made by that guy from 2005. This is a more recent implementation, but as you can see, there's a lot of error in the, I really don't know if it's OpenStreetMap. Oh, it is Google Maps. You can see Google here. Anyway, so they're using Google Maps. The prediction of the person's location based on satellite is really off, but the IMU corrects it quite well. And you can see that there is some drift, although we're assuming that Google Maps' grade part here is accurate, but I don't know if that's the case. But it does seem like there's quite a bit of drift. Either the map itself is bad or there's a lot of drift, or both. So anyway, these are just this is just a cool idea, and you're free to look at the paper if you're interested. But he's just walking around and it's tracking him, and it is hard from it's hard from this video to tell how much drift there actually is, but cool idea anyway. And here is some other example. Oh, whoops. Where they attached, well, they had this IMU which they had taped to the guy's foot, or they rubber banded it to his foot, and it tracks him moving, walking in a straight line. Kalman filters are pretty common as a correction tool. That's true, but they are more of a correction tool. They can't really do much prediction by themselves, I believe. So I don't think any of these methods use that as, like, most of the methods that we'll see don't use any kind of filtering as, like, the fundamental understanding of how these algorithms work is not based on the filtering. The filtering is something that you do in post. But you do usually use some type of filter, so that's true, I guess. Anyway, this dude's walking upstairs. Moving on. Here's that paper from the Oculus Tracking paper. Well, this is the info from the Oculus Tracking paper. My brain is breaking today. It's Friday. This is a cool read, and it just describes how you can do the tracking with more than one method. You can use like a gyroscope, accelerometer, magnetometer, things like that. Here's an example of where you would use filters with drift correction. But even so, drift correction, if most of these sensors are only measuring deltas, and deltas, like, they will accumulate no matter what. I forget what the name of the method is. Crap, I don't remember. There's some method that's used in robotics to try to also, it's not a filter, but it tries to figure out how much error there is in the prediction. But again, these only have so much accuracy. So there is always going to be drift no matter what, and filters sort of help. And this other method that I can't remember the name of helps, but they can only do it so well. And you need some kind of, you need a more stable prediction, which we'll see soon. Anyway, a bunch of trackers used to track the Oculus Rift, and these are still used. And IMUs basically include all of these at once and somehow synchronize them usually. So as for image-based tracking is nice because it does, if you're trying to measure if a pixel has moved, it's usually easiest to measure it with respect to a video frame, especially if they're very small or something, or there's only so much rotation between frames or minor translations or something. I don't know what I'm saying, that doesn't make any sense. Anyway, to figure out if something moves in a video, we track features. A lot of you are in the computer vision class, you already know this. For example, you try to figure out where one feature is inside of another image or frame. For example, where is the top of his head in the next frame? Optical flow is a set of techniques that you use to find how much a feature has displaced between two frames. And there are a lot of continuity assumptions which help you make some, they help you figure out how confident you should be about that is the right feature that I should be tracking. KLT is a common method of doing this. People who have taken computer vision have definitely seen KLT. I believe it's a topic that usually gets covered near the end of these classes. But this is an example of KLT tracking where the pixels are moving. You can see that there are some errors, definitely, especially when he rotates. Because, as we'll see in a second, depth is not accurate. And here's another example of somebody trying to track their body, and you can see that there is still a lot of errors. Although this was a class project, I think, so I don't know if there are any errors just in the interpolation or in the implementation. But, you know, you can still sort of see how the features are being tracked, even if there is error. He's also not moving that much. Anyway, image-based tracking is pretty easy to implement because we do have so many APIs that do it already. Like I already mentioned, OpenCV, Vuforia, things like that. If you can recall this video, hopefully, of somebody trying to do this on a smartphone. So they're trying to do the 3D reconstruction using only a single camera view, and it kind of works, and they can eventually play a game with it. You can see that there's quite a lot of drift though, or just jitter in general, which is not ideal. And filtering would help with this drift part probably, or not with the drift, but the jittering itself. It would definitely help smooth it out. You can also use interpolants, like splines, to figure out at least how to smooth out the jitter. It won't fix drift though. And we have the ambiguous depth problem, which I'll talk about in a second. Anyway, this cool paper we saw before. So why isn't image-based tracking enough? Well, first of all, especially those of you who are in a computer vision class who have tried to implement this, you'll know that feature matching with pretty high confidence in only these 2D images that you probably used converges really slowly. They can take quite a few iterations to figure out if one feature is the same in another frame. Also, feature detection in general requires some pretty decent specs, otherwise it will take forever. And AR and MR devices, especially ones that are mobile, are not strong, so there will just be a lot of latency trying to do it this way. like you won't get the prediction until, or you'll drop a lot of frames of prediction, or a prediction won't be updated for a couple of frames, or any of those kinds of problems. Also, in image-based tracking, we have problems with motion blur and other visual effects like auto exposure, autofocus, which can distort the image between frames and make it harder to find feature correspondence confidently. And I kind of touched on this before, but depth is ambiguous in 2D images. Like, how do you know? I don't know if there's a good example. You already know what a city looks like, so this isn't a good example, but I don't know. Say like from the think like a camera, and think like, is this gun? Well, this isn't a great example. Imagine if you have a ball in front of the camera. How do you know if it is a very small ball that's very close to the camera, or a gigantic ball that is very far from the camera? You might be able to use some monoscopic cues to figure that out, but there will still be some ambiguity. And in order to track a 3D world, we need to be a little bit more confident in that. I also touched on this a few times already, but where pure AR and MR diverge is in mixed reality, you're trying to use real world mechanics to guide virtual world mechanics, so you actually do need to know where real world objects are, but in pure AR you don't. Although in a much earlier slide I said that we should just, for the purpose of discussion, just assume that AR is any. At least when I talk about it, I just say that AR is any situation where the real world is visible. Anyway, I want to move on because I don't want to spend too much time trying to clarify these. So I mentioned last time that we would talk about reconstruction today, and we will. So reconstruction is a hard topic, and you can find a lot more details in classes like computational geometry, numerical analysis, and so on, which the CS department does offer, although they're mostly grad classes. So the first point of discussion is depth sensors, which are exactly what they sound like. They try to figure out this ambiguous depth dimension. Specifically, they try to figure out the depth of each pixel in the image. They try to create what is it's called an RGBD image, so RGB plus depth. A lot of the times, as most of you probably know, most images are RGBA, so there's an alpha channel. A lot of the times what RGBD images are just RGBA images, except alpha is used to store depth, and whatever alpha is used that actually affects RGB originally is like baked. I mean, there are equations that will bake the values of RGB. Anyway, that's not important at all. You can do this, or you can create these sensors in a couple of ways. You can use structured light, and where is my image that shows this? Huh, maybe I forgot it. Structured light is when you try to shoot a pattern. Here we go, copy image, put it here. Nice. Structured image is when you try to shoot a pattern of light at an object and you figure out how the object deforms that light. These can be quite susceptible to interference because if you have other sources of light that can distort the pattern, or if you have other things that can distort the pattern at all, or distort the sensing of the pattern, it will break your reconstruction. You can use calibrated stereo cameras, which is what we normally use, which are these cameras which are synchronized. These cameras like this, which are synchronized and calibrated. So in this case, you have an RGB camera and an IR sensor. An IR sensor is usually a camera. It's just that, or at least it's presented to you as the programmer as a camera. It's just grayscale. In any case, these are calibrated and synchronized. Synchronized meaning that they know when or they try to render out the image at the same time, or at the very least you know how much time has passed since they rendered their images. We'll see examples in a second of common stereo cameras. LiDAR sensors are basically really high-end structure light sensors, which are used in applications like space tracking, like trying to reconstruct the moon and things like that. So, or even just like localizing planes and things like that. These LiDAR sensors try to, well, they still send light patterns out, but they send patterns that are recognizable at very long distances, because as you probably know, most light doesn't travel too far. Like if you have a really weak IR light, like one that you could buy off Amazon for like $5, the red dot is not going to last for a very long distance. So LiDAR sensors are much more powerful than that. Anyway, those aren't that important to us. Some popular depth sensors are the Kinect. So this is the Kinect V1, which came with the Xbox 360. It didn't work very well, but from a research perspective, this is arguably the first consumer depth sensor that was not thousands of dollars. So it was really useful for research on reconstruction. This is the Kinect V2, which came out with the Xbox One. Most people know about the disaster that was trying to force people to buy an Xbox One with it. But even so, these are still really good depth sensors, and they work with Windows 10, whereas I don't think the Kinect V1 does. And more recently, we have the Kinect Azure, which is these little pod-shaped depth sensors, which have very high. Well, we'll talk about point clouds in a second, but they can generate really dense point clouds and reconstruct really thin objects and things like that. So these are awesome. We just got some of these recently in the lab before the quarantine. This is a RealSense, which is pretty similar to the Kinect, except most people would consider it easier to work with, but it has a much smaller range, like its field of view, I think, or how far it shoots its IR rays is a lot shorter. I don't remember exactly how the internals are different. They are much smaller cameras than the Kinect, definitely, and I believe that all of the individual cameras are much closer to each other. Therefore, it reconstructs objects which are much closer to the camera, but it does them at a much higher density than the Kinect does. So this is all to say that the RealSense is designed to reconstruct very small objects. It doesn't do great with much bigger environments like rooms. That's what the Kinect would be for. The Leap Motion has an even smaller range of what it can reconstruct. It's specifically meant for hands, but the API is really good at tracking hands. So this thing here is a Leap Motion, and this is the Leap Motion broken down. It has these two little IR sensors. And in this case, it only has IR sensors. It doesn't have an RGB camera, so everything is always in grayscale if you're trying to get the image directly. Whereas the RealSense does have an RGB camera, and so does the Kinect. The iPhone 10 is probably the first consumer smartphone that had depth sensors. That's how they were doing like the 3D emojis and face, like using your face to log in at like with higher security or something. I don't remember how they advertised it. But this also has a depth sensor inside of it. You can see it has an IR camera, has an IR illuminator, and its regular RGB camera and things like that. And finally, there's the structure sensor, which is this sensor you've probably seen in the lab, and it's this cool little sensor that you can put on an iPad. And there are apps like It Sees 3D, which can reconstruct people using this sensor. And this is also like an RGB camera, and I don't remember if these are the IR. Well, this is an RGB camera. I don't remember if these are the IR cameras or if this is the IR camera. This looks more like an illuminator to me, but it doesn't matter. It's a really cool depth sensor that can work on mobile devices, which I believe it's one of the only depth sensors that's buyable that works on a mobile device. So they're cool. So point clouds, the whole point of depth sensors is that they're trying to generate point clouds. In general, a point cloud is just a bunch of 3D vertices, which may or may not have vertex colors. So, for example, a regular 3D mesh can be converted to a point cloud by just removing all the edges and polygons and just keeping the vertices. In the context of reconstruction, most of these points, most of the vertices are 3D feature correspondences. So I think I have an example of epipolar geometry later on, but with epipolar geometry, you can, if you have multiple cameras which both recognize a feature and you decide that they are the same feature, you can use epipolar geometry to figure out where that point is in 3D relative to the cameras. The standard file format for point clouds is PLY, which Blender can read, and Unreal and Unity can't read them, but they can be converted to other formats. If you gather point clouds from depth sensors, they're usually really, really noisy because it's pretty random which features correspond to which, and in any given frame, like which features you can actually recognize. And sometimes you can track them with something like KLT, but with really complicated tracking systems like AR devices, which can move freely throughout pretty much anywhere in the real world, this is not, it's questionable. Like, the performance is not as good as just recording or tracking features through a video that is recorded from a camera that doesn't move that much. If point clouds do have vertex colors, you can generate a texture like a UV map plus a diffuse map from these vertex colors, and the density of the points affects how good that texture is. And the density, like how many points you can generate, is affected by things like interference and reflections and how good the depth sensor is and latency and things like that, which we'll talk about later. The challenge of point clouds is how do we create the mesh so that we can use it in other applications? And we need the mesh because it's important for geometric algorithms, which are important in general because we use them for a lot of optimizations, but they're especially important in applications like surgical reconstruction. You need a mesh to render things usually. Even rendering this point cloud is done by trying to, basically tries to create a mini mesh that is visible. Like you expand, for example, like maybe you expand the point into a sphere or something like that. And you also need a mesh to do like collision detection. So if you have this guy and you want, let's say in the HoloLens, you want to throw a ball at somebody who is real, and you want the virtual ball, you're throwing a virtual ball, and you want the virtual ball to bounce off of that real person, you need to somehow generate a collision mesh for them. So moving on to how we get the mesh, this is called reconstruction. And we'll talk about a few different reconstruction methods, but the more robust methods are really important for things like dentistry. Like, for example, retainers are usually made by reconstructing your teeth after braces. They're used for brain scans and things like that. We'll see some examples in the next slide. Some common methods of doing reconstruction, just some very common high-level methods. We'll see a couple of good examples soon. But some of these, or the two most common ways of doing this are with computational geometry. We'll see triangulation soon. And fitting implicit functions, which is it's a more recent method that is starting to get much better performance than computational geometry in real time. So these are kind of cool, exciting methods. It's almost like the 3D version of fitting splines to things. These more robust methods that are made for like surgical applications are not really meant to be run in real time, but in AR we actually do need it to run in real time. So we do a couple of things to cause this to happen. For example, we can reconstruct with lower resolution point clouds. What happened to the rest of my text? Anyway, I don't remember what this said, but we can use lower resolution point clouds. We can do it stochastically, where we choose a certain random set of points. There are a couple of ways to do this, which we'll see soon. This is an example of some surgical reconstruction. So you can reconstruct the skull and these brackets that are being put in there. This was for a liver reconstruction project. Here you have like teeth, and I guess they're doing some kind of jaw reconstruction. Or I don't know what they're doing there. It looks like jaw reconstruction to me, but I don't know. I'm not a medical person. Anyway, some geometric methods. A very old and relatively popular method, especially in surgical reconstruction, is called vertex switching. It's based on graph theory, so your 410 material, or I guess your 283 material. Is 283 graphing? Is 283 graph theory? I don't even remember. That class wasn't very memorable. Anyway, one of your graph theory classes. Vertex switching basically tries to create a closed graph of vertices that it contains all of the vertices, and it also doesn't have any intersections. That's like a very high level explanation of what they're trying to do. It still has arguably the best reconstruction quality. I cited it somewhere, but there's a really good paper that compares reconstruction quality and performance among a couple different methods. But vertex switching has arguably the best reconstruction quality. It's arguably the slowest though. It works really well on sparse point clouds, so point clouds where you actually don't have that many features. A lot of other methods don't work with sparse point clouds, which is a problem that modern research is trying to deal with in a real-time fashion. Vertex switching is really slow. It's basically the bubble sort of reconstruction because it basically tries to do pairwise comparisons between vertices to figure out, like, which edges will cause it to meet these requirements, like no intersections, try to contain all the vertices and so on. So cool method, not really feasible for AR. Moving on to more modern methods. A lot of modern methods are based on this concept called Delaunay triangulation, which was proposed in 1934. These are a bunch of algorithms which try to create a mesh with a bunch of triangles which don't intersect. So there are a bunch of resources that I provided for you if you are interested in how this works, but what it does is it tries to create a triangle using 3 vertices. If the circumcircle, so the circle that encompasses the triangle, doesn't encompass some other triangle, therefore trying to prevent the triangles from intersecting or being too dense, I guess. There are usually a lot of different solutions to this problem, and what these will usually generate is called a convex hull. So it's a mesh that encompasses all the points that is also convex. So for example, the mesh collider, when you check convexing unity, for example, it generates a mesh that encompasses your really complicated visual mesh. Unreal 4 calls this a simple collision. In Unreal 4, the complex collision is a collision that is basically the mesh itself, like with the points, but not important, just a cool thing to know. Voronoi diagrams it's basically a mesh that is constructed using the center of Delaunay triangles, or I think that's what it did. It might be like the epicenter or something, or some other definition of the center. But anyway, these are very related concepts. In fact, they're duals, so you can convert between them pretty trivially. And each possible solution to this problem is called a seed, and this idea of seeds is used in destruction physics a lot, so that you can make a bunch of different destructions. And Delaunay triangulation is the foundation of most of this field of computational geometry nowadays, because it's the foundation for most of the algorithms that we'll see. It's pretty fast, and it's pretty stable, and you can do a lot of interesting things with Voronoi diagrams, but that's out of the scope of this class. So ball pivoting is a really popular reconstruction method that is based on Delaunay triangulation. What they do is they basically roll a ball of some uniform size between the vertices like this, and it creates an edge if the ball can actually reach another vertex given its size and the distance between the vertices. And if it can't, then it will just create a flat surface basically. So for example, if this vertex here were missing, the ball would roll around instead, like around the inside of this mesh, because it would just miss. The goal in this case is to create the outer hull, so the part of the mesh that you would actually see. We don't really care that much about the inner if you won't see them anyway. And also, if if you're generating point clouds based on real objects, you usually won't be able to get points that are inside the object unless something is wrong, like mirrors, for example. We'll see an example of this problem in a second. My voice is dropping. I am getting a... Yeah, Discord is complaining. Is it still dropping? Is it still bad? I am recording this, so... Type faster. Oh, the warning from Discord stopped, so I don't know. I'm pretty sure Spectrum is throttling connections, and it happens every so often. Like, I noticed that it happens pretty, like at pretty regular intervals where the internet will just drop for whatever reason. It's really annoying. Anyway, I'm recording this. Anyway, I don't know what you missed exactly, but ball pivoting, you're trying to roll a ball that is a uniform size around the vertices. It creates an edge between vertices that are reachable given this ball rotating, and you were trying to create the outer hull, and there's a really fast and common method, and it works best with uniform density clouds, meaning that the distance between vertices are pretty much the same. You can imagine why this is a good idea, because if you don't have uniform density, for example, if you're missing, let's say that this was sampled at a different distance, like each of the vertex distances are much different than the vertex distances of the outer part of this. The problem is that it would be hard to find a ball size that will actually be able to reach the entire, or roll around the entire outer hull. Fortunately, we can, a lot of depth sensors actually do generate pretty uniform density clouds. And if the cloud is dense enough, then it's usually not a problem anyway. It's good for general purpose reconstruction, and unlike most of the other methods that we'll see, it doesn't really make any assumptions that the mesh is closed, which is especially good for AR because we're trying to reconstruct things that are not closed, like walls or your desk, but it doesn't have a completely, like for example, a depth sensor. If you were wearing a HoloLens right now, your depth sensor wouldn't be able to see the underside of your desk, so it's fine if it reconstructs the top part as being flat. I don't know if this is a part that you missed, but if there are missing vertices or if it's not uniformly dense, then the ball might just miss and it will create a flat volume, which is okay for things that are not closed. So moving on, Power Cross is it's a really nice, robust method that is unfortunately not great for AR. What it does is it guarantees a watertight mesh, so a mesh that doesn't have any holes in it. Unfortunately, in AR we do deal with a lot of holes like mirrors, so it's not great for us, but it's still a cool method if you're interested. What it does is it creates a Voronoi diagram with the points, and it makes spheres that are as big as possible that can fit inside of the set of points without touching any of the points. And it does that, it does that everywhere. It does that inside the mesh and outside the mesh because it actually doesn't know where the mesh is yet. And the assumption is that the spheres that get really, really big can only get that big because they're outside of the mesh. Therefore, they're unconstrained. And so with that, it can create the watertight mesh. You could see that just like in ball pivot, we are using spheres again because they're nice for figuring out like the distances between vertices. Anyway, the idea here is that there will be a clear separation between the inner mesh spheres and the outer ones because the outer ones will become gigantic. And you can create this interesting thing called a medial axis, which is generated from the center of all the spheres. And the medial axis can be used for things like skeletal recognition or shape recognition. It's just a very simplified mesh that kind of approximates the 3D reconstructed mesh, but obviously it would have much fewer polygons than a full 3D reconstruction. It's a really slow method, but it's really, really robust. And there are techniques that are similar to stochastic gradient descent, where you just choose a random number of points, which help a little bit. but this is a very popular method and it's really good. Before we move on to the implicit function strategies, recall this slide on splines. Splines are these interpolants that have a certain amount of differentiability, and interpolants they basically try to predict a function between data points. So if you have a bunch of data points and you don't know what function was used to generate them, you will just try to guess a function that works. And I don't know if you remember the answer to this, but differentiability is important because it lets us merge a bunch of predictions without creating any holes or sharp edges. It lets us create a very smooth surface, or in this case a line. In games we use Bezier splines, which have control points like this that you can pull and change the tangent, but it's not important. Here's another example of a spline in 3D where you have this helix. The points are fitted with a helix, which is a pretty good approximation. Anyway, moving on. For surfaces, we have the radial basis function, and moving least squares is another very similar concept. These are surface interpolants, which means that they are similar to splines, except they try to interpolate along a surface as opposed to a line. And what they try to do is find some continuous function. And if you recall 3D calc, you can describe a surface with a function, like a sphere. Anyway, you try to find a continuous function that will wrap around all the points, or at least approximate them pretty well. And in deep learning type strategies, you have these activation neurons which measure how close the point is to the function, and you can use that to learn the function itself. So implicit methods try to learn the implicit function. In this case, the implicit function can be the radial basis function or moving least squares. And it tries to create this function by figuring out, it iteratively tries to figure out how far the points are from this function. And given the depth of your network, you might only be able to measure a certain order. You might only be able to predict a certain order of function, the order being how complicated it is. And these methods aren't particularly fast yet, but they are becoming very close to real time, which is cool. As of 2020, they work at like 5 frames per second, which is still a lot better than these other reconstruction methods. So one very common, how many slides do I have left? I might go slightly over just to try to finish this up because we are pretty close to the end. A very common implicit method is called Poisson surface reconstruction. It tries to create the implicit surface by using the normals. So the normals tell you which way a point is facing. So for example, if you shot an IR, an infrared light at a surface and it stopped at that point, you know that the normal must be facing towards the camera to some extent. That's some naive way of doing it. But anyway, the point cloud capture itself will generate these normally, but they, no pun intended, they're not always accurate. In graphics, we need normals to know which way the outside of the surface is. So for example, in assignment 3, I used the normal to figure out which way to push the vertices of your face. Sometimes you can pre-process them by making the assumption that you can make an assumption about what the inside of the mesh is and assume that the normals always must face outwards. For example, the medial axis that we just talked about is good for this. This will not work if the normals are not well oriented. So if in this case, well, let's say the normals are just facing random directions, then Poisson surface reconstruction won't be able to do it accurately. These are popular for closed surfaces because, like I said, on a closed surface, you know which way the normal should point because it will face the camera. Here are some examples of closed surfaces. Anyway, it's a very popular method. It's not great for open surfaces. In fact, it doesn't work at all for open surfaces, but it's still a cool method. And that's actually the only implicit method that I'll go over because it's so popular. And there are these more recent methods, which you're free to look at the papers if you're interested. So some hard reconstruction cases include thin surfaces, because in the case of a thin surface, the point cloud is so sparse that you can't really accurately reconstruct it. Only very, very recent papers, such as Chabra 2020, which was published from a UNC student, only very recent papers can actually reconstruct thin surfaces. So he was making this comparison here, where like here's the actual input, like here's what it should reconstruct, and their method reconstructs it pretty well, although they make it a little bit too thick, but it's a lot better than these totally failed cases. And here we actually have two thin surfaces. We have the actual legs of the table, and we have these rings. So only recent methods like this 2020 paper can actually do this. Reflections are problematic because they will cause the infrared rays to reflect, so you can't really reconstruct a mirror. But there are some really cool papers like this one from Facebook that you can check out where they actually take advantage of the fact that it's a mirror to reconstruct the part of the environment that's behind you. So that's a kind of cool idea. There is light interference, like just visible light interference, which can obscure the texture, like if there's too much glare. For visible light spectrum, lights like your typical fluorescent light or whatever you're using, your energy efficient light bulbs, they won't really affect IR rays, which is why depth sensors usually use IR. But you can also have IR interference, which will obscure any of the infrared rays or might give you false positives. For example, if you have some other depth sensor that is also pointing at that object, that is also generating rays which can confuse the other depth sensor in the system. So this is a problem if you're trying to do really complicated reconstruction and you want multiple depth sensors. The rest of this I think I'll go over next time. So yeah, that's it. Bye.